but how are we supposed to get into a calculation to know how to get that?
An important note, people. This is my YouTube channel. This is yesterday's video. There are 33 of you in this room. Why are there only 15 views? You're supposed to watch the video so that you know what we were going to cover yesterday. Watch the video. Because we're moving on today. If I take away all the technology you have, I can ask you to give me a rough idea. What's square root of 27? Square root of 17. 4 point something. Square root of 27 will be 5 point something. How do I figure out something? The following idea is about 3,000 years old. This is not new. I'm just going to phrase it in the language of calculus. The advantage is that I think about a continuous function, a differentiable function, as being smooth. What do I mean by that? Well, I mean, when I look at a close-up, it looks like a straight line. We talked about this where we talked about what it meant to be differentiable, and you couldn't have a corner or a cusp or a gap or a jump. It's smooth. If you zoom in far enough, it's a straight line. So let's consider for a moment the graph of the square root of x. I said I wanted the square root of 27. Angela, you said 5 something. Why 5 something? Bingo. Square root of 27 is close to square root of 25. And I know the square root of 25. So I say to myself, out here at 25, I know exactly this value is 5. So if I want to know the square root of 27, I really just need to move that point over. Just need to move the dot. But I don't know exactly how to move that dot. But if I were to take a real close-up here and zoom in around that point that we've just labeled, the graph of the square root of x would be very similar to a line. And not just any line. But what line? The tangent line. How do I find the equation of the tangent line? I need a slope. How do I get the slope of that tangent line? Derivative. Okay, wait a minute. The slope, wait, it's not just f prime of x, it's actually f prime of 25, right? For this line in particular, it would be f prime at the point we're looking. That would be the slope. And I know a point. So I have the point, and I have the slope. That's sufficient to get me the equation of a line. That's all I need, point and slope. I know the equation of my tangent line L, is y minus the y value equals m x minus the x value. That's all I need. If I take the 5 from the left and move it to the right, this is a function. You pick an x, plug it in, you get a y value, and it's roughly the square root of the x you put in. I want square root of 27. I can put 27 in this, I'll get you the square root of 27. Or at least something reasonably close to the square root of 27, because that line is reasonably close to that curve. Let's do that. What's square root of 27? Using this to approximate it. Well, it means I need f prime of 25. What's my derivative? One half to the negative x to the negative one half. Great. That is 1 over negative powers go in the bottom. A 1/2 power is a square root. There we go. So f prime of 25 1/10. So if I want square root of 27, I just put 27 in there. Gesundheit. What do you get? Which is 5.2. 26 over 5. Am I right? If I'm wrong, how wrong am I? What's square root of 27? I'm off by less than 0.004. 4 parts in 1,000 using nothing but a straight line. That's a pretty damn good approximation, isn't it? No, it only goes through the 0.525. Right, it's tangent line. Because I'm not actually solving for the y value on the point. What I'm doing is I'm using exactly. Here's the graph of some arbitrary function, our point A, f of A. In our case, we were looking at 525. Look, in this little neighborhood around A, can you tell the difference between what's on the line and what's on the curve? Oh, hell no. And if I zoom in, well, maybe I could see a little bit of a difference the further away I get from 25, right? But as long as I'm close to 25, this works perfectly well. If I wanted the square root of 17, I don't think it would be good to use that point as a base. If I wanted the square root of 17, what would I do? I'd switch to 16, because I know the square root of 16. So I could do this entire process again, only changing the point of tangency I'm looking at. This idea can be done in general. And this function that we came up with right here, this is a straight line. It's called the linear approximation of the function, in our case, the square root of x, at our point, or at x equals 25. I can say it either way. If I want the square root of 35, I'll probably not use x equals 25, I'll probably use x equals 36. Want the square root of 120? Nope. Because in this picture, doesn't matter which side of A I'm on, that's really close on either side, isn't it? Because that's what a continuous and differentiable curve looks like. When you get in close, it looks like a straight line. This is probably best, we'll describe best in a little bit, when I'm really close to whatever my value here is. In general, the linear approximation of f at A. You take f of A, well, in our case, that was the 5. You figure out the slope, and then how far off do you get from the x value you want to look at? Now, when I first saw this expression, I thought about this like a slope. Let me go back to the definition of derivative. What's the definition of derivative? F prime of A equals limit definition. I know it's been a long time since we did we can do it anyway. Limit as x goes to A of f of x minus f of A over x minus A, right? That's my limit definition. Well, in that case, if I got rid of the limit itself, I would say that the derivative was roughly f of x minus f of A over x minus A. And this is where the approximate idea comes into play. I'm approximating without that limit there. Watch what happens if I rearrange this equation. I multiply the x minus A to the other side. I move over the f of A. F of x is roughly equal to f of A plus f prime of A times x minus A. And this was exactly the expression we called the linear approximation. It's really just the tangent line. But it's a great rough number. What is the square root of 17 using the approximation? Wait a minute. Emily, you said did it matter whether I was on the left or the right? Let's do the square root of 15 instead. I suppose technically I shouldn't write find. I should write estimate. Because I'm not getting an exact value. I'm getting a rough value. Let's estimate the square root of 17. 50. Well, if I use the function the square root of x, just like we did before, I know the derivative of that. We already worked that out. What's a number near 15 whose square root I know? And the square root of that. So I put the square root of 16 in, I get 4. F prime is 1 over 2 times the square root of 16. I get 1/8. And that means that the linear approximation formula, f of a plus f prime of a, x minus a. So if I want to do 15, the square root of 15 is roughly 4 plus 1/8 times 15 minus 16. Well, that's 4 minus 1/8, or 3.875. How close am I? Not bad, man, not bad. Again, I am off by less than 0.003. 3 parts in 1,000. If I need it to be tighter, I'm going to have to do a lot more work, right? But let's think about why this is off by what I'm off by. If I look at the graph of the square root of x, I'm looking at what's going on near 15, right? That's here. Zoom in. There. It's not perfectly straight, is it? But it's really close. As a matter of fact, I apologize for not having a color version of this, but let's graph the line we were just looking at. The equation of our line. Let's graph that. 4 plus x minus 16 divided by 8. Instead of writing the 1/8 in front, I wrote it at the end. Where's the difference? Too small for the eye to see, right? So if I'm okay being off by 0.3%, it's better than I've done in most lab courses ever, I'm good. The larger the value of my derivative is, in this case, sorry, the smaller the value of my derivative, the more straight line we get, because a small derivative means a very small change in slope. But this function, when I zoom in, looks really, you can just barely see that there are 2 pixels lit up vertically right here and right here. They are starting to spread apart just the barest little bit. But I'm looking up there at 15. I'm not even close to what's going on down there. Questions? Yes, ma'am. Exactly. I need to have a value I know exactly nearby. And then I can work off of that. That's the whole point of using a point I know to then work with. And it doesn't have to be a square root. It can be any root you want. The algorithm for finding a square root in this fashion was known in Babylon about 4,000 years ago. It wasn't written in calculus terms or in tangent line terms at all, but this idea can be found in cuneiform. That's how old it is. Pre-hieroglyphics. More questions? Let's change functions. Hmm? 0.1 is close to 0, and I know sine of 0. That's when I know 100%. Sine of 0 is good. And I also know the derivative. What's the derivative of sine of x? And cosine of 0. There should have been a chorus, people. Cosine of 0 is 1. What's the linear approximation function I have here? Okay. I start with the value. It's f of 0 plus f prime of 0 times x minus 0. F of a, f prime of a, x minus a. Wait a minute, yeah. Y equals 0 plus 1 times x minus 0. That's just y equals x. So sine of 0.1 is 0.1, roughly. Son of... Why should I have already known that sine of 1 would be about, sorry, 0.1 would be about 0.1? I need you to go all the way back to August. We started talking about limits, and one of the very first limits we actually computed, we did with a table. What limit did we compute that involved sine of x? No, that was a square root, the one where the calculator borked on me. Further back. Aha! Page 85, we showed that the limit of sine of x over x was 1. That means sine of x over x is roughly 1 when I'm close to 0. By the way, we used 0.1 as one of our values right there. We've done this. By the way, why would I give a flying about this? Who cares that sine of 0.1 is roughly 0.1? There are 13 of us in this room. Without this idea, we'd be blind. Somebody tell me Snell's law. Snell. Where these numbers and variables mean what? What's n1? What's n2? What's theta 1? What's theta 2? Picture some barrier. In our case, a piece of glass. Light comes in at some angle, theta 1, hits the glass. What happens? It bends. It refracts. Now, depending on the two indices of refraction, N1 up here and N2 down here, this angle will change. I've always seen this written as a ratio, where it's sine of theta 1 over sine of theta 2, and then N1 over N2. So I think I may have some indicators different than the version you learned. The reason we need this is because light is coming into my eyeball, and I'm bending it before it gets there. As long as the angle at which I am bending it is a small angle, I can ignore the sine of theta. And I can change this to simply read N1 theta 1 equals N2 theta 2 when theta is close to 0. When I'm looking at a small angle like that, like 0.1 radians, 0.1 radians happens to be about 6 degrees. I don't have to worry about trig functions at all. I can ignore them completely. And I can use x instead. This is called first order optics. And until computer-controlled lens design was the best way to make a pair of glasses, was the best way to make lenses. And this goes all the way back to Galileo and further back. If we really look at lens development and reading glasses in 500 BC. Greek reading glasses, in this case, consisted of a large ball of clear glass put in a mount and held over the piece of paper. It was a spherical lens. So instead of having a flat barrier, a round barrier. Radius of curvature is exactly how we get modern glass design. So those of you wearing contact lenses, I couldn't count you, so I don't know. If there's somebody in here with contacts, you count too. It's the whole point of this. Applications out the wazoo. As my angle gets bigger, this condition is going to break. So how close is close to zero? Let's talk about that margin of error for a second. Let's consider the difference between the two. If I wanted to know what angles were useful to count as close enough to zero, I would need to know where this is small versus where this is big, right? Graph that. How much of an error are you willing to tolerate? This is a legitimate question. Tell me, how close is close enough? Doesn't this sound familiar? This is our epsilon delta idea again, isn't it? How close is close enough? How far apart am I willing to let these two be?
That far because it's this direction. Like, you could, or
Yeah, but I just need to know how far. What's your tolerance level? 0.1, 0.01, 0.001. How close is close enough? Let's go with 0.01. I'm going to say I can be off by 1%. I want to know what X values go with the Y value 1%. Just like our epsilon delta idea. I'm going to put in negative 0.01, and I'm going to put in 0.01. Now I'm going to have to change my window to see this properly because those values are really, really small, and that's 1. So I need to zoom in quite a bit here. So let's zoom in. And I'll give you a factor of 10. Since I'm looking for 1%, we'll go as high as 10%, as low as minus 10%. We'll put the marks every 0.01 so I can see them. And I'm pretty sure I don't need to go all the way out to negative 2 pi and all the way out to 2 pi. I'm really only looking at angles that are less than 90 degrees. So let's make our x's go from minus pi over 2 to pi over 2. Now when I look at this graph, I can see the range of x's that are permissible, the range of angles for which this estimate is good enough. What is the positive angle where these two graphs cross? How do I find that x value? Say again? Jonathan? I could do a secant line, but I can actually find it exactly. I'm just going to ask the calculator, where do these cross? And to do that, it's under second trace under the calculate menu. Option number 5 says intersection. I just need to remember to tell it the right two graphs. The first one is the curve, sine of x minus x. See, if I walk over here, I'm on the right part. I hit enter and it labels it, little plus sign there on the graph. And then it jumped to the next one in my list, which happens to be the one I want to look at, negative 0.01. I hit enter again, and it asks me, well, where do you think they cross? So I walk over until I think I'm close to it, and I hit enter again. 0.392, all these ugly decimals. Hang on a second. There's my answer, 0.392. But that's in radians. What is that in degrees? That was in the review section, man. Back in the trig. Oh, crap. That's it. I did tell you we needed to remember back to August. Aha. To get from radians to degrees, I multiply by 180 and I divide by pi. So I multiply by 180 and I divide by pi. Angles up to 22 degrees. In either direction, positive or negative. I'm only off by 1%. Quick. From top to bottom. I want you to hold your hand out in front of you, move it down until you can just barely see it. What angle down is that if you're looking straight ahead? Just over 40 degrees-ish. 40, it's not quite 45 degrees, closer to 30. I'm still in focus. Even using an approximation, I'm just barely out of focus down there. Same thing up above. If I look at my angle of ascension rather than descension, I get the same result. I got a field of view about 45 degrees wide, where I'll be in focus with a linear approximation. How close is close enough can really give me quite a wide range of values that still work. Once this idea was put forward, index of refraction, I don't know what, somebody look up Snell and tell me when it was. When did Snell's law get popularized? The internet is your friend, people. Google for me. $1600. 400 years ago, we had this idea, and I can make it work better without any technology. So for 350 years, we were grinding lenses by hand. And this was the best we could do. 325 years. I'm pretty sure we started grinding lenses mechanically in the 50s. Again, I'd love to tell you this is useless bullshit. You're never going to use it again. I can't see without it. Now, a question I cannot answer this semester, but can answer with calculus. Why does the light bend? There's an absolutely beautiful video by 3 Blue 1 Brown on why the light bends as it goes through from one item to another. And it's because the light hits stuff and is absorbed and re-emitted and absorbed and re-emitted. And that transfer of energy causes molecules to wiggle. And the way molecules wiggle is a differential equation. It's an equation involving first and second derivatives. People, we can do this. You have the math you need. I'll put a link to the video on our Canvas page. Questions? Yes, ma'am. Yeah, 22.4 degrees. That's the limit at which we're no longer within 1% of the correct value. So if I hit 22.5 degrees, I'm now more than 1% away from sine x just by using x. It's our tolerance. We decided 1%. That's my line.
Is that
Yeah, that's right here. Trace. That's that spot where they meet. They're more than that far apart. That's our delta for the epsilon we chose. I can also think of it as an error, right? And I talked about this when we talked about how far off I could be. What's my allowable error? We did this with the square roots as well. When I do an approximation, what I'm really saying is that if I think of dy dx like a fraction as opposed to a limit, then that's a rough equality. And if I think of this as a fraction, then I'm really thinking of dy and dx separate from one another. Well, that kind of makes sense, right? Because we had the little triangle that we were looking at for the slope of the secant line, and then we let the ratio of those two things, and we let dx get smaller and smaller. That was our h going to 0. But I can think of them as if they were separate items. When we were looking at the square root of x, we took the derivative. And the derivative is 1 over 2 root x. But if I think of dy and dx as separate ideas, I can think of measuring the change in y based on the change in x. That's what a slope does, right? So let's rewrite this and write dy is 1 over 2 root x times dx. Hey, wait a minute. The rates of change are related to one another. That's yesterday's video, people. There's just no d over dt here, is there? It's the same thing we did yesterday. We're going to call these differentials. dy is the differential of y, dx is the differential of x. And then I can think of these as separate items. And this kind of looks like the chain rule. Hey, wait a minute. We had one function of another function, right? We had f of g of x. I can think of f in terms of g, take the derivative of the outside, leaving the inside alone, and then g in terms of x. df dx was really df leaving g alone, and then dg dx, and damn it, don't those two things cancel? The chain rule is built into this differential idea. But this got sparked in my head by your comment about error. What does this mean to be off by, right? Once again, I go back to lab science classes. Propagation of error and error calculations, right? I want to measure the volume of a sphere. What is the formula for the volume of the sphere? Once again, I'm going to chastise some of you people. This was the first example in yesterday's video. Formula for the volume of the sphere. Anybody got a ruler? What's the finest measurement available to me on your ruler? Centimeters. So if I'm in centimeters, when I measure in centimeters, I'm going to round to the nearest tenth of a centimeter, right? You've got little marks between the centimeters. That's millimeters. So I can get to the nearest millimeter, which means I could be off by half a millimeter either way. So I measure my radius, and my radius comes up to be 21 centimeters. Exactly. Once again, exact, quote unquote. If I'm measuring with your ruler, it could be as much as a half a millimeter bigger or a half a millimeter smaller, and I would have rounded to 21.0 because that's the number of sig figs I can get off that ruler. So I'm going to put down the error, plus or minus 0.05 centimeters. So here's my question. What possible error propagation occurs when I go to calculate my volume? How far off can my volume be based on this error in my radius? How am I supposed to know that? This measurement is R, this 21 centimeters. This is a change in R. So let's think of this as R and this as dr. And when I'm asking you how far off is my volume, I'm really asking for what's the change in V based on this change in R. All right, wait a minute. How the hell do I get dV alone? I don't. I start by doing dV dr. That's the derivative of this thing. What's the derivative? Not yet, but if I move that dr over, and now you can put in all the numbers, right? And you can tell me the maximum error possible in my volume. I'll use the positive version, but if you want, you could just put a plus or minus in front of this whole thing. And you get dV is 4 times pi times 21 squared times 0.05. Notice R is in centimeters, dr is in centimeters. This result is in cubic centimeters. That matches the units for volume. I want to know change possible error in volume. I'm going to end up with a number of cubic centimeters. Somebody give me a number. No, give me this number. What's the value of this? I could be off by a quarter liter. Is this a big error or a small error? What's relative error? Oh, it's error in terms of my measurement, isn't it? So if I want to do relative error, I do dV over V, which, by the way, I could do before I plug in the numbers. 4 pi r squared dr over 4/3 pi r cubed. The pi is going to cancel. 2 of the r's are going to cancel. The 4 is going to cancel. The 3, it's on the bottom, so it'll come up to the top. 3 dr over r. If you work out the relative error in advance of doing the propagated calculation, you've saved yourself a step. I know every one of your lab reports is supposed to contain a discussion of what are the potential sources of error. How did that error propagate through your experiment? Ladies and gentlemen, this is how we do it. I will repeat my comment from earlier. I want that view number to go up by the end of the weekend. Watch the video you should have watched yesterday. If you came in late, I have your homework. Come get it. I'll see you later.